All right, we are on the chapter there. We've been talking about types of reactions, and last time before the exam there, we were talking about something. There we go. We were talking about types of reactions. Remember, there's really two big classification reactions that we talked about. There are double displacement reactions, and double displacement reactions, again, are always two ionic compounds together. And that is pretty much how you can recognize it as a double displacement reaction. And again, they will switch partners and they will make two new ionic compounds on the other side. And double displacement reactions really account for 2 of the 3 reasons why a reaction takes place. There is a more specific classification, which is a precipitation reaction, where one of these guys will make a solid, basically, or a precipitate. The other sort of more specific classification is acid and base neutralization reaction. And in those reactions, essentially, one of these guys will basically go that way, basically make some water, basically. And that's, again, 2 really of the 3 reasons why reaction takes place. Either you formed a solid, you made water, or the third reason where we got into last time is redox reactions. And redox reactions are a transfer of electrons that's occurring. And that's really the third reason why a reaction takes place. And in a redox reaction, as we talked about last time, there is a oxidation reaction and there is a reduction reaction, and they always occur together. So something gets oxidized, somebody else gets reduced, and then somebody gets reduced, somebody else gets oxidized. There are several definitions of oxidation, but we'll just roll this time around here with a loss of electrons, and reduction means somebody has gained electrons. Again, sometimes people remember that Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Some people like the oil rig, oxidizing is losing, reducing is gaining type of thing. Now, when something goes through oxidation or goes through reduction, we can sort of figure out what is happening by simply looking at sort of like a number line. And to the right of 0 there are positive numbers, to the left of 0 are negative numbers. And we could compare, really, when we look at an equation, we could compare the element on the left-hand side of the arrow and the element on the right-hand side of the arrow. And we could look at what is really known as its oxidation state. And when somebody gets oxidized, they lose electrons, which means they actually become more positive. So if you look at the oxidation state of an element on the left-hand side versus the right-hand side, and if you just follow it on like the number line and it's heading towards the positive side, then that substance is going through oxidation. The opposite is true if somebody gains electrons and gets reduced. They then have more electrons than protons, which means they're going to be more negative. So if you compare that element on the left-hand side of the arrow to the element on the right-hand side of the arrow, and you look at their oxidation state, you will see that is becoming more negative, and that is something that is going through reduction. So if you can correctly sort of identify the oxidation state or number, which we'll talk about in a second, how to properly sort of do that, you can sort of figure out what is being oxidized and what is being reduced. The nice thing about this is, again, they always occur together, which means if you can just for sure figure out what is being oxidized or for sure figure out what is being reduced, then the opposite thing is happening to the other guy that's there. So as long as you can figure out at least one of them, you can sort of figure out what's going on with the other. As we'll talk about, the oxidation state is not necessarily the charge that we always associate with an element in an ionic compound, but it is sort of the charge they take on, depending if they're sort of sharing electrons, what charge they would have in that situation. Thank you. Now, another thing we talked about is the oxidizing agent. The oxidizing agent is the substance that gets reduced. And it's called the oxidizing agent because when it gets reduced, it has to gain electrons. And the only place it can gain electrons from is somebody else that gets oxidized. So it causes the oxidation in the other substance that allows it to accept the electrons and be reduced, while the reducing agent is a substance that gets oxidized. And it's sort of the same definition. It's called the reducing agent because when it gets oxidized, it's going to release its electrons, and somebody else is going to pick up those electrons and then get reduced. So it's causing the reduction in the other substance. Now, when you're asked the question of what is being oxidized, what is being reduced, and what is the oxidizing agent or the reducing agent, those are different questions that you're being asked. Also, all four of those things, if you need to identify them, are always found on the reactant side of the arrow. So on the left-hand side of the arrow is where you're going to find all those guys, what's being oxidized, what's being reduced, your oxidizing agent, and your reducing agent. When we look at something like magnesium plus some oxygen, making some magnesium oxide here, again, if we look at the oxidation state, remember that anything that is uncombined, element-wise, not combined with anything else, will basically have an oxidation state of 0. It's only when, like, for example, a metal and non-metal get together that they will form those charges we commonly think of. So in this case, on this side here, the magnesium has a +2 charge on the right and a -2 charge for the oxygen on the right. So if we again look at the magnesium, it started at 0. And on the right-hand side ended at +2, which means it's moving in the right-hand side there in the positive direction. So again, in this case, it is being oxidized. The oxygen here is starting at 0 and ending at -2, which means it's moving in the negative direction, becoming more negative, and the oxygen here is being reduced. That would mean in this example, our O2 is our oxidizing agent, as that is the substance being reduced. And the magnesium here is our reducing agent, as that is the substance that is being oxidized. Question on that there. Now, we also talked about that you could split off equations into what are referred to as half reactions. So if you had something like this equation here, where we had our 2 magnesium plus our oxygen going to our 2 magnesium oxide, you could write 2 half reactions. We could take our 2 magnesiums going to our 2 magnesiums with a +2, and this would be our oxidation half reaction. It would have 4 electrons, and that is the oxidation half reaction. Here we have 2 magnesiums going from 0 to +2 here. We have 2 magnesiums. Each one's going to lose 2 electrons, so that is why we have a grand total of 4 electrons happening here, 2 for each of the magnesiums. If we take our oxygen here, it's going to pick up those 4 electrons. Again, 2 electrons per oxygen will create 2 oxide ions in this case, and this is what is known as the reduction half reaction. Now, when you have half reactions, they are called that because when you add them back together, you get the overall reaction that's happening here. When you have a half reaction that's an oxidation half reaction, the electron should always be on the product side. And when you have a reduction half reaction, the electrons should always be on the reactant side. That is because when we look at the product side, it would be like the electrons are being given off or lost. So for oxidation, electrons end up on the product side like they're being given off. On the reactant side there, it's like the O2 is gaining those 2 electrons, which is basically your definition of oxidation. So when you see electrons on the reactant side, that is definitely a reduction half reaction. Now, when you have 2 half reactions like this, you can add them back together. But the one thing that you always have to make sure of before you add them back together is the electrons in both half reactions should always be the same number, because the idea here is however many electrons somebody loses is the exact same number of electrons that somebody gains. So In certain cases, if you have two half reactions that you want to add back together, you sometimes need to multiply a half reaction by a number to get the electrons to be the same. So for example, if my first half reaction had 1 electron and my second one had 2 electrons, I would need to multiply the top half reaction by 2 all the way across everybody to get me to 2 electrons so that we have the exact same number. Sometimes you actually have to multiply both half reactions by a number to get them to the same. So for example, if my first half reaction had 3 electrons and my second one had 2, common number there is 6. So what I would have to multiply my top one by 2, that's to multiply my bottom half reaction by 3. Again, not just the electrons, but everybody there would get multiplied by that number. Once you do have your electrons basically the same in both half reactions, we could add them together, and you could think of like the arrows as like an equal sign. So anything on opposite sides of the arrow that are the same will completely cancel out. The electrons should always completely cancel out. It's like subtracting 4 electrons to each side. Then once you do that, if you have something on opposite sides of the arrow that are the same but do not completely cancel out, you could still reduce them down. So they don't necessarily have to always cancel out if they're on opposite sides of the arrow, but they could reduce down. For example, if you have, say, 4 waters on one side of the arrow and 2 on the other, you could basically subtract the 2 to the other side and be left with 2 waters when it's all said and done. Once you have everything canceled out or reduced down, everybody on the left-hand side of the arrow stays on the left-hand side of the arrow, and everybody on the right-hand side of the arrow will stay there. In this case, since we have 2 ions that are going to come together, those 2 guys will come together and make our ionic compound, a magnesium oxide in this particular case. When you look at the half reactions, they should be balanced 2 ways. They should be balanced like a normal equation, which means you have the same number of elements on each side. So for example, I have 2 magnesiums on each side. They also should be balanced in terms of overall charge on both sides of the arrow. This guy has basically no charge. That is +2, and 2 is +4. And here the 4 electrons would supply -4, and that adds up to 0 on both sides. So it is balanced on both sides. Everybody adds up to 0 on the right. Everybody adds up to 0 on the left. And we got 2 magnesiums on each. Same thing when we come to the bottom. We have the 4 electrons before I cancel them out. That's a -4. The oxygen is 0. So that is a -4 on the bottom left. On the bottom right there, 2 times -2 is -4. So again, we're balanced in terms of -4 on the left and -4 on the right. They do not have to be the same, or they do not have to be 0 on both sides, but they just need to be the same number on both sides when you look at the overall charge. And obviously here we have 2 oxygens on each side there. Any questions on any of that stuff? I think we talked about last time. Yeah. All right. So let's talk officially about how to assign oxidation numbers. Oxidation numbers are also sometimes referred to as oxidation states. And essentially, there are some rules that we look at. As I mentioned before, they're not always going to be sort of especially with our sort of nonmetals, they're not going to be always the negative charge that we associate with them when they're in an ionic compound. Now, the charge, this would be the charge the atom would have if all the electrons were completely sort of shared and transferred, or really transferred. The first rule is, as we talked about, any element that pretty much is naturally how it comes, not combined with anything else, will have an oxidation state of 0. So that's always going to be 0. If you have any type of ion, for the most part, if you have just an ion written there by itself and it's like a lithium with a +1 charge, then the oxidation state would also be a +1 charge. If you had an iron 3 ion sitting there, the iron 3 would have a +3 oxidation state. So if you have just an ion that's there, whatever the charge is on the ion will be the charge or the oxidation state for that guy as well. Now, oxygen is usually a good place to start if you have oxygen involved and you want to assign oxidation numbers. That is going to be -2. The only exception is if it is really not oxygen, but it's actually peroxide. So if you have something like hydrogen peroxide or something like that, it actually will be a -1 for the oxygen. I will say that in most cases, if you see oxygen, it's probably a pretty safe bet. It's going to be -2. I would say hydrogen peroxide is probably the only one, maybe sodium peroxide. How do you know it's really peroxide and not oxygen? That 2 that's there hangs around. So that extra 2 kind of hangs around and kind of tells you it's going to be peroxide rather than just oxygen. Like I said before, in most cases, probably safely assume it's going to be -2. Now, when we're assigning oxidation states and we have 3 elements, I'll just call it A, B, and C for creativity purposes here. Usually if we got 3 elements and we want to assign oxidation numbers, the general rule is go right, go left, save the guy in the middle for last. Yeah, so save the guy in the middle for last, go right, go left, save for the guy there. If you have just 2 elements and you want to do an oxidation state, I would also go right first and then go left next in most cases. I would definitely, if you have oxygen in there, start with that, regardless of where it's at. That would be where I would start if you have oxygen. So those are sort of the general rules if you're sort of assigning oxidation states. Now, if we have hydrogen, it's going to be +1, except if it comes after a metal. In that case, it's going to be hydride. It's going to be -1. Everybody in group 1 is going to be its normal +1 charge or oxidation state. Everybody in group 2 will also be its normal sort of +2 oxidation state, just like its charge. Fluorine, which is the most electronegative element, will be -1. When you add up all of the oxidation numbers for all the elements that are present within the molecule or the ion, it has to equal the charge. So if you have something that has no charge, it's neutral. When you add up everybody's oxidation numbers, they need to equal 0. Now, if you have a polyatomic ion, for example, that has a -1 charge, when you add up all the oxidation numbers for the elements within that polyatomic ion, it needs to equal -1. So whatever the charge may be is what they have to be. For the most part, oxidation numbers will be whole numbers, but they can actually be fractions. Like in superoxide, -1/2 could actually happen as well. So let's take a look at how we would approach something like bicarbonate here. So we have here, again, a 3-pack of elements happening. I'm going to start on the right-hand side. In addition, I'm going to start on the right-hand side because, frankly, that's oxygen. So that's a super good place to start when you're assigning oxidation state. That's oxygen, which means its oxidation state should be -2. There are 3 of them, which if we're thinking about our negative charge here, is going to give us a grand total of -6, 2 for each of them, right? And there's 3 of them. Now, this thing does have an overall charge of -1 bicarbonate, which means when I add up all my oxidation numbers, it does need to equal -1. Now, I'm going to go to the left-hand side. Again, I'm going to leave the one in the middle for the end. So left-hand side, that is hydrogen, which is +1. So I have a +1 here. So now I leave the guy in the middle. It needs to add up to -1. And in this particular case, we now have +1 and -6 is going to be a -5, which means my carbon in this case should be what to get me to -1? So if I have a -5 right now, what do I need to add to it to get to a -1? +4. Yeah, if I do a +4 there, +4 -5 equals -1. Everybody is good in this case, yeah? Question on that there. Now, when we give the oxidation numbers, a couple important things. For hydrogen, it should be +1. You should include the plus, not just write 1. When you do it for carbon, it should be +4. When you do it for oxygen, it is just one of the oxidation states on one of those guys. It is -2. It is not like -6, the grand total. So when you're asked to give the oxidation state or number of something, it is if you just took the one guy by itself, sort of what its oxidation state by itself is, not the cumulative charge of everybody together. Any questions on that there? All right, so why don't you try some here? Here's a periodic table with lots of oxidation states. Like I said before, some of these guys we normally think of as being like -1, -2, -3. You can see they can be pluses in certain cases, especially something like chlorine. So we might have touched upon it last time. Again, if you have chloride and an ionic compound, its oxidation state is going to be -1. But if you have chlorine that's attached to some other things, like some oxygens, because of the difference in electronegativity, the other elements may pull the electrons away from the chlorine, and that's going to cause chlorine to become more and more positive, right? Because it's losing electrons. Hasn't completely lost them, but not shared equally, going to be pulling away, going to make the chlorine more and more electron deficient and more positive. And it will take on, if I put this L there to make it chlorine, it will take on a more positive oxidation state because it's actually sharing electrons with things that are more electronegative, and again, kind of sucking out the electrons from it. Any questions on that? So that's why when we have covalently bonded nonmetals, we oftentimes get, again, oxidation states that don't match those like negative ones that we always assume. We get the negative ones in ionic compounds because they're gaining those electrons completely, so they become negatively charged. All right, so for each of these, assign the oxidation state for each element present. Okay, so let's take a look. See, again, I'm going to start here with the oxygen on the right. That's a -2. There are 3 of them, which gives me kind of like a -6 going on. There's no charge on this thing, so I know when it's all said and done, it does need to equal 0. I'm going to go to the left-hand side. That's group 1, which means it has a +1 oxidation state. That means in this case, if I add up my +1 and -6, that's a -5. And since it does have to equal 0, my I here is going to be rolling with a +5 in this particular case. Any questions on that? That is because the I is covalently bonded to those 3 oxygens, which are more electronegative and sucking the electrons towards it. And that's going to cause the I in this case, because it's sharing electrons, to become more positive than normally what we associate in the negative version. Coming here to the IF7, I'm going to start with fluorine, which is always going to be -1. That's going to give me a -7. Once again, no charge overall, so it needs to equal 0. So in this case, my iodide here is going to be my iodine is going to be a +7 oxidation state in this case. So once again, here for sodium, +1, I +5, and O -2. I +7, and fluorine -1. Here, when it gets attached to fluorine, which is the most electronegative, and 7 of them, we see that the I goes to in a higher oxidation state because those fluorines are going to bring the electrons towards itself, again, causing the I to be more electron deficient and more positive as they're moving away. Lastly, here, you're going to start with the oxygen on the right. That's going to be a -2. That's going to give me a -14. Once again, this is neutral, so that's going to equal 0 when it's all said and done. You can go to the left. That is potassium, which is +1. There are 2 of them, which gives me a +2. If I add that together, that is +2 and -14. That is a -12, which means my chromiums needs to be a grand total of +12 in this case to balance it out. But it is not +12 for the oxidation state of the chromium because there's not 1 of them, but there are 2, which means 12 divided by 2 is each one is a +6 in this case in terms of its oxidation state. So the potassium here would be +1, the chromium would be +6, and the oxygen would be -2. Any questions on how to assign oxidation numbers? Again, a really important thing, especially when you're dealing with redox reactions, to be able to understand what is being oxidized and what is being reduced. These are what you would compare on the left-hand side of the arrow to the right-hand side of the arrow, the same element, and see what's happening. Is it becoming more positive and becoming oxidized, or is it becoming more negative on that number line and becoming more reduced? Any questions on that there? All right. So now that we talked about sort of redox a little bit here, that is the big classification of reactions, but you can classify redox reactions more specifically. So the first type of classification is a combination, or sometimes referred to as a synthesis reaction. And in a combination or synthesis reaction, it is basically two things make one thing. So that's a classic sort of synthesis reaction. I got two things making one thing there. So that is a combination reaction. I have sodium plus chlorine making sodium chloride. That is also two things make one thing, a combination or synthesis reaction. So a more specific classification of this reaction is a synthesis or combination reaction. This is still a redox reaction happening. The aluminum here on the left, 0 in terms of its oxidation number. The bromine, that is naturally how it comes on the left, so that also is 0. When those two guys get together, the aluminum on the right ends up with a +3. The Br ends up with a -1 in this case. So again, if you roll a little number line, if you're not sure, aluminum started at 0, ended at +3, becoming more positive. That means the aluminum is being oxidized. The bromine started at 0 and ending at -1, which means it's moving to the left, becoming more negative, and that means that it is being reduced in this case. Yeah. That would also mean that my reducing agent would be which thing? My reducing agent is the aluminum. It is the thing being oxidized. And the oxidizing agent is the bromine, the thing being reduced in this case. Again, as you can see, the thing being reduced, the thing being oxidized, the oxidizing agent and the reducing agent all found on the left-hand side of the arrow. Yeah. Now, another more specific classification of a redox reaction is a decomposition reaction. And frankly, a decomposition reaction is the opposite of what the synthesis is. So synthesis or combination, you put it together. Decomposition, you basically break it apart. You start with one thing and make a couple or more things. So you're basically doing the opposite reaction here. If you take some potassium chlorate there and you heat it up, it will make potassium chloride and oxygen gas. That's two things that came from one thing. That again is your classic decomposition reaction. Now, this is also still a redox reaction because if we look at the oxygen here, that's a -2. The potassium is a +1. That equals 0, which means that is a -6 overall, a +1. The chlorine here is carrying a +5 oxidation state here to balance it out to 0. All right. We go on the right-hand side, that is potassium with a +1 charge. That is actually chloride because that's an ionic compound, so that is its normal charge. Oxygen by itself has no charge or oxidation state. Once again, if you look at your number line here, you can see if you look at the chlorine, started at +5, which is over here, and ended at -1, which is moving in the left direction, right? Becoming more negative. It is the chlorine here that is being reduced as it is becoming more negative. It is the oxygen here that started at -2 and ended on the right-hand side at 0 that is becoming more positive. So it is this oxygen right there that is being oxidized. Yeah. By the way, what is happening with the potassium? Anything? Nothing's happening with the potassium. It's +1 on the left, +1 on the right. It is a spectator ion. It's just hanging out for the ride. It's floating around in the solution. It's not really doing much. So this is still a redox reaction. It is more specifically called a decomposition reaction one thing breaks apart into many, pretty much your opposite of a synthesis or combination reaction. Questions on that there? If you're not sure, the Cl would be our the Cl would be our oxidizing agent, and the oxygen here would be our reducing agent in this case as well. Now, a combustion reaction is another type of oxidation reduction reaction. The general definition of a combustion reaction is the only thing that you really need is this guy right there, oxygen, O2, technically speaking. I will say that probably if you're talking to somebody in your natural conversation with somebody and you're talking about combustion reactions, which could happen daily, I suppose, they're probably not going to be talking about this type of combustion reaction. They're going to be talking about like when you light a Bunsen burner combustion reaction, which is you take an organic guy and you add oxygen to it and you get CO2 and water. Like methane, when you do light your Bunsen burner there, make CO2 plus some water, a little 2 action there, maybe a 2 action there as well. So I would say 9 times out of 10, this is sometimes referred to as an organic combustion reaction, and that's usually what most people are talking about. But frankly, that is really all you need for it to be a combustion reaction. So here we do have oxygen, which makes it a combustion reaction. This is going to be 0, right? This is also going to be 0. The oxygen here is -2. There's 2 of them. It's -4. The sulfur will be +4 in that case. Again, to get it to 0 in this case. We look at what's happening here with the sulfur. Sulfur started at 0, ended at +4, becoming more positive. The sulfur here is being oxidized, right? The oxygen started at 0, ended at -2, which is becoming more negative, and it is being reduced. This is our reducing agent. That is our oxidizing agent in this particular case. So it is definitely a redox reaction. Electrons are being transferred, which is ultimately why this is happening, but it is more specifically sometimes called a combustion reaction. This is the guy we saw earlier, also a redox reaction, also a combustion reaction because there's oxygen. Both of these reactions could also be classified as 2 things make 1, yeah? So you can look at either of these reactions. This could be a synthesis reaction because 2 things make 1. Could definitely be a redox reaction because electrons are being transferred. And frankly, they have oxygen, so you could classify this guy as a combustion reaction as well. So there can be ways you can classify the same reaction multiple ways depending on what you're looking at. I would always say just choose the best one for the situation in terms of what you're looking at in terms of classification. But you definitely can classify the same reaction a number of ways depending on what you're looking at. Any questions on that there? Now, a displacement reaction is another type of redox reaction, and more commonly, this is sometimes referred to as a single replacement reaction or displacement. And in a single replacement reaction, A plus BC, you have something that is either a metal that has no oxidation state and an ionic compound. These are the type of reactions we did way back when we did the halogens and the different layers and moving from the top layer to the bottom layer when we did that experiment. If this is a metal, it will come in and kick out the positive guy and form a new ionic compound. And that guy that comes out will actually have no oxidation state. Much like we saw when we did that reaction, we can start with a non-metal and an ionic compound. And that non-metal will then go kick out the negative guy and make a new ionic compound. And that guy that comes out will have no charge. Remember, for these reactions to actually take place, whatever is coming in needs to be more reactive than what it is replacing. So A in this case needs to be more reactive than what it is replacing. If it is not more reactive, then the reaction will not take place. So you can, even with these single replacement reactions, get even more specific in the classification. This is what is referred to as a hydrogen displacement because the strontium, no oxidation state, -2, +1, comes in and kicks out the hydrogen. When it does so, hydrogen becomes 0, and that gets kicked out and a new ionic compound is forming here. And the strontium, in this case, becomes +2. So here the hydrogen is changing from +1 to 0, and the strontium is going from 0 to +2. It is being oxidized to strontium. It's becoming more positive, and this is a redox reaction, obviously, that's taking place. This is sometimes referred to as a metal displacement. Metal, as we just said a second ago, will come in and kick out the metal. This has 0. This is +4. That is -1. On the right-hand side, this guy is 0. That is +2 and -1. In this case, the magnesium is going from 0 to +2, being oxidized. The Ti is going from +4 to 0, which means it is being reduced. It's actually becoming more negative. If you're not sure, again, if you follow number line, +4 is over here, 0 is moving in that direction. It's becoming more negative. It's being reduced. In this case, the chlorine is actually a spectator ion. It's -1 on both sides. It's not doing much in this particular case. This last one is a halogen displacement, which is kind of like that experiment we did. 0, +1, -1, +1, -1, 0. Here it's going to kick out the negative guy. And obviously we get our redox reaction here and our single replacement. So double displacement is the only one where there's 2 ionic compounds. Single replacement, you have 1 ionic compound and like something by itself, a metal, a non-metal, or something like that, basically reacting. Any questions on that there? Now, again, how do we know if a reaction is going to take place or not? There is what is referred to as an activity series. That's a fancy activity series. A non-fancy activity series usually just has elements listed with hydrogen somewhere in the middle and elements above listed, elements below listed. And when you look at just a basic sort of activity series, anybody higher on the lists will replace anyone lower on the list. And vice versa. Anybody lower on the list will not replace anybody higher on the list. So in a basic sort of activity series, that's sort of how you do it. This gives you a little bit more specifics, which is, you can get a replacement with just water, or you need something a little stronger than water. You need some acid for it to actually occur. So if we look up here at calcium and hydrogen, we could see that if we find calcium is right here, all you need is just cold water to happen, and that is what we have there. So this reaction will take place. It's very water reactive. But if we try to do lead with water, lead's down here, with water, it's not going to work. But if you did lead with some acid, that's enough for it to work. So there is a difference, and this reaction will not take place. And again, like I said, if you had a basic sort of activity series, higher replace lower, lower doesn't replace higher, basically on the list. Yeah. Any questions out there? Now, we did the halogens when we did that experiment. If you remember, reactivity in group 7 on the periodic table increases, right, as you go up. What we saw was chlorine replaced bromine, bromine replaced iodine, iodine didn't replace anybody, right? So that was the one that stayed purple the whole time. If you remember back to that experiment 3, I think it was. And fluorine is most reactive. So reactivity increases in group 7. That is your ohm activity series for the halogens, again, increasing as you go up. So in this case, we want our chlorine to replace our bromine. So that is going to happen because chlorine is higher in group 7 than bromine. But if we try to do the iodine to replace the bromine, iodine is less reactive than the bromine, and it would not take place in this case. Any questions on that there? Now, another type of redox reaction that occurs that sometimes confuses people is this one. It is what is sometimes referred to as a disproportionation reaction. And that's a fancy way of saying that the same element in the same reaction will both be oxidized and reduced at the same time. So it happens a lot in atmospheric chemistry with chlorine. In this case, our chlorine over here starts at 0. Over here, the chlorine actually has a +1. So in this case, the chlorine is going from 0 to +1. It's becoming more positive. It is going through oxidation there, right? Now, if we look at this chlorine, that is -1 in the chloride. And on that chlorine, it is going from 0 to -1, becoming more negative. This guy going to this guy is actually going through reduction. So the chlorine in this case is both being oxidized and reduced. How would you write your half reactions? Well, you would start with chlorine on one side and ClO- on the other, and the other half reaction would start with the same thing, the chlorine on the left-hand side and the Cl- on the other side. Then you would do some balancing that we'll talk about here in just a second to balance it up. Any questions on that? The hydrogen on the left is +1. The hydrogen on the right is +1. And the oxygen on the left is -2. And the oxygen on the right is -2. So that's -2. That's +1. That's -2. That's +1. Nothing going on with those guys. It's actually just the chlorine here that is actually being both oxidized and reduced. That again was referred to as a disproportionation reaction. Basically, the same element does both things, gets oxidized and reduced in the same reaction. Any questions on that there? All right. So oops. Here's some reactions. This is basically a precipitation reaction based on solubility rules. That's going to be a solid. It's basically from a double displacement reaction. This is really the net ionic equation we're looking at here. This is a base. This is a generic for an acid. That's an acid-base reaction happening. Also a double displacement reaction. This is what we just saw there. That's a hydrogen displacement or a single replacement reaction. And this is two things that make one thing. That is a synthesis or combination reaction. Questions on any of those there? So to sort of summarize what we've been talking about here in terms of reactions, again, there are two big categories. We have our double displacement. And again, underneath that umbrella, more specific classifications, precipitation and acid-base reactions. Again, those account for, as we talked about a number of times, solid and water being formed. Under the redox umbrella, where we have our electrons being transferred, we have all the other classification reactions. Synthesis falls under there. Decomposition falls under there. Single replacement falls under there. And combustion reactions fall under there. So those are, again, more specific ways of classifying reactions, but ultimately there are electrons being transferred and a redox reaction basically happening. Any questions on any of that there? Okay. All right, that wraps up this. Just something being oxidized, right? And something being reduced, as we talked about, this being your oxidation half reaction and your reduction half reaction. Again, we know that because the electron's location runs on the right, which should always be the oxidation on the product side, and the reduction side, like they're being gained, should be on the reactant side. Again, before, if you just have basic half reactions, you need to add them together. As I mentioned before, we will have to perhaps multiply by a common number. That would give us 2 electrons along with the 2s for everybody else. electrons should always be the same. Then you could add them together like we did earlier and basically cancel them out. Now, when we're dealing with redox reactions in acidic or basic conditions, it requires a few more steps along the way to do these. So first off, the first thing that you want to do is split your reaction into these half reactions. So you should end up having an oxidation half reaction and a reduction half reaction. I would also perhaps, before you do that, maybe a step before that, is figure out who is being oxidized and who is being reduced. So I would do some oxidation numbers and try to figure out first off who's being oxidized and who's being reduced. It's really helpful as you do these problems that when you get to a certain step, you'll know if you're doing that step correctly, if you already know, which one's oxidized and which one's being reduced. How do you split them off into the half reactions? You should not overcomplicate it. You're just going to take the two elements that are the same on each side of the arrow and put them together in a new reaction, basically. So if you have an Mn on the left and an Mn on the right, you take those two guys down and you put them together. Kind of like what I just did with the chlorine. There was like a chlorine on the left and a chlorine on the right. I put those guys together in a reaction. Chlorine on the left, the Cl minus on the right. I put them together when you do that. Once you do that, you then want to balance all elements other than hydrogen and oxygen. And how you're going to balance them, you're going to use coefficients, just like you're balancing a regular old run-of-the-mill equation. So if you happen to have two sulfurs on the left and one on the right, you're going to lay up a big 2 coefficient in front of the sulfur on the right, and you're going to balance everybody like you would. Once you've balanced all the other elements with coefficients, just like a normal equation, now we're going to get to the part where you go, huh? And then we're going to get to the part where we're going to balance the oxygens. And the way that we're going to balance the oxygen is we're going to add water to balance the oxygen. So if you have, say, on the right-hand side, like one oxygen in something, it doesn't be by itself, but in any format, one oxygen. And maybe on the other side, you have like 2 oxygens with something else, right? So say H2O2 and maybe like Li2, right? We're going to balance the oxygens here by adding water, and we would need to add water to the left-hand side because it has 1 oxygen on the left and 2 on the right. When I add water to balance the oxygens, what else comes with water besides oxygen? There are 2 what? Hydrogens. So for every water that you add, you then need to add 2 H pluses to the other side. So you're going to add water to whichever side needs the oxygens to balance out the oxygens on each side. And then however many waters you added to the other side, you would need to add 2 H pluses. So in my example here, I would have to lay up a couple of H pluses there on the right-hand side to balance out the hydrogens that are in the water. If you don't do that, when you're all said and done, you're going to be short some hydrogens. By the way, if you ever start out with a half reaction where there is unequal numbers of hydrogen on one side versus the other, you could just add the H plus to the other side that needs it, however many you need. So you could just right off the bat, if you see like you have HNO3 on the left-hand side, and you got like NO2 on the right, and you're obviously different hydrogens to begin with, you can right off the bat just throw a H plus on the right-hand side, and that will make sure that you balance out the hydrogens. So sometimes you might need to do that as well. All right, so we're going to add water to balance the oxygens. We're going to add H plus to the other side to balance out the hydrogens that we put in there. At this point, we're going to then balance the charge on each side I should say each side, each half reaction. And we're going to do that by adding electrons. So we can only add negative electrons to balance out the charge. So what do I mean by charge? I mean that when you add up the charge overall, I'll use my bad example here. I got H2O plus some lithium oxide, right? Lithium 2 oxide, put a 2 there. And I got on this side a little peroxide, and I got 2H plus. So if I wanted to do this step, what I'm looking for is to make it as simple as possible. Sometimes people are taught to look at each element and see what's happening with each element. But frankly, that is a waste of time because we know now that the oxidation numbers need to add up to the overall charge. So the math is actually done for you. What I mean by that is the overall charge on this with all its oxidation states is 0, right? When you add them all together. The overall charge on this guy is 0, right? When I add up all the oxidation states. Overall charge on this guy is 0. Overall charge on this is +2, yeah? So on the right-hand side or left-hand side, I have a 0. On the right-hand side, I have +2. In this example, since I could only add negative electrons, which side should get the electrons? I would need to put 2 electrons over here because that's now going to give me a -2. +2, -2 equals 0 on the right and 0 on the left in this case. And now we will be balanced. Does it have to equal 0 on both sides of the arrow? It doesn't. It just needs to be the same number on both sides. So sometimes people think it has to get to 0 equal on both sides. It doesn't. It just needs to be the same number on both sides. And that's the easiest way to do it, not think about how many electrons somebody lost or how many electrons somebody gained. Because the overall formula takes into account all the oxidation numbers, it pretty much does the math for you. So just look at the overall charge of everybody and add it up on the left and add it up on the right, and then you can balance it. Once you do that, the last thing that you want to check is that you have the same number of electrons in each half reaction. And if you do not, then you need to multiply, right? Like we just did earlier. So if you do not, you need to multiply by a common number. Lastly, you're going to add both half reactions together. The electrons should completely cancel out. Again, that's the part where opposite sides of the arrow, same thing, cancel or reduce down. Everybody on the left stays on the left, everybody on the right stays on the right. If you do all those steps, congratulations, you just balanced it in acidic conditions, yeah? One of these reactions. Basic conditions, we'll talk about in 1 second how to go to basic conditions, but these are the steps to do for acidic conditions. Any questions on that there? All right, so that's a lot of words. Let's actually do one here together so you can see how you put all this in place. So let's take a look at this reaction here. I'm gonna rewrite it actually as iron and dichromate, I think. Dichromate. What was it? It was 2, 3, and then 3. So that is a 2. That goes to iron 3 and Cr2 plus, I believe. Make sure I got that all right. 3 plus. 3 plus. There we go. 3 plus, 3 plus, minus 2 plus 2. Perfect. I give it a little bit more room here. All right. So we're going to take this reaction here. And we have basically iron 2 going to react with dichromate to form iron 3 and chromium 3. So the first thing I really want to do is figure out what is happening here in terms of oxidation and reduction. So if we assign some oxidation numbers here, my iron here is +2, right, which is the charge on it. This is the one we just did in that problem, right? So the oxygen is -2, which gives us a -14 equals -2. That is the one where each of these chromiums ends up at +6, right? We did that one a second ago, +12 overall, right? Now on the right-hand side, my iron is going to be +3, and my chromium is going to be +3 as well, because again, it is basically just the charge on the ion. Any questions on how I got to those oxidation numbers? This is important because now hopefully I could identify what is being oxidized in this case. If I look at the iron, it starts at +2, right? Ends at +3, which is heading in that direction, becoming more positive, which means it is being oxidized, right? Again, the good news is by default, that would mean the chromium here is actually being reduced. I know that because if I look at the chromium, it starts at +6, which is over here, and ends at +3, which is moving to the left, becoming more negative and being reduced. Yeah. That would mean in this case, my oxidizing agent is, it is the chromium, or the dichromate here is my oxidizing agent. My reducing agent here is the iron 2. Any questions on that? All right, now that we got really what's happening here, the first thing we want to do is split this reaction into its two half reactions. By the way, we're going to balance this in acidic conditions, right? So the way you do that is you just take the two elements that are basically the same on opposite sides. So I got an iron on the left and I got me an iron on the right. So that is one half reaction. I have a chromium on the left there in Cr2O72 minus, and on the right, I have a chromium with a +3 charge, right? So those are my two half reactions. Now, because I already identified what's going on here, I know my iron half reaction is the oxidation half reaction, and I know my chromium half reaction is the reduction half reaction in this case. So the next thing that we want to do after we split it off is we want to balance all the elements except for hydrogen and oxygen. So when we look at the iron on the left, we have one iron. And when we look at the iron on the right, we have one. They have different charges, but there's just one iron basically there. When we look on the second half reaction, there are two chromiums on the left. And how many on the right? Just one. So just like a normal equation, we need to balance it up there with a 2 in front of it. Any questions on that there? Now that I've balanced all the elements besides oxygen and hydrogen, oxygen is where you want to go next. So we're going to look at the top half reaction. There's no oxygen on either side. We don't need to do anything with it. So we don't have to put anything in it because there's no oxygen. When we look on the second half reaction, there are 7 oxygens here on the left. And how many oxygens on the right? 0. So the side that needs the water to equal the oxygens is the right-hand side. And I would need to add the exact number of waters to oxygens that I need, which in this case is 7 waters. That's going to give me 7 oxygens on the right-hand side. Because I added water, I just put how many hydrogens there on the right-hand side? 14. So to the left-hand side, to balance it out, I have to add 14 H pluses. Any questions on that there? All right, so we've now balanced all the other elements. We've now balanced oxygen, and hydrogen is balanced as well. What is now left to do is we want to balance out the charge on each side of the equations. And we're going to do that by adding electrons, which are negative. So we're going to look at overall charge on the left for the top. Since this is the only one there, that is a +2 overall, right? On the right-hand side, that is a +3. Which side needs the negative electrons? The right-hand side. How many electrons do I need to balance it out? Just one. With that one electron, that gives me a -1 for a grand total of +2 on the right to match the +2 that I have on the left. Now, if I come down to the bottom half reaction, that's 14 H pluses. That's going to contribute a plus 14. 14 times plus 1, right? Or 14 times plus 1. Yeah. The dichromate has an overall charge of -2, which means it's going to contribute a -2. And if I add those together, 14 and -2 leaves me a net of plus 12. Yeah. If I go to the right-hand side, the chromium with a +3 charge can contribute how much? +6, right? 2 times +3. The water is going to contribute 0, right? It's neutral. Which side needs the electrons here? The left-hand side needs the electrons, right? How many electrons does it need? Does need 6 electrons, right? 6 electrons will give me a -6. -6 and plus 12 yields me a +6 that matches the +6 I got going on the right-hand side. Yeah. First off, any questions on the electrons, how to add them? So you need to add the electrons to whichever side will balance out the charge. So this is the point where knowing what is going on is really helpful to you, because I know that this is my oxidation half reaction, right? And when I have an oxidation half reaction, the electron should end up on which side? Products. So that's good. You added it to the right side there, right? And when I have a reduction half reaction, the electrons should be added to the left-hand side, or the reactant side, which is what you did. So that is a way that you could check to make sure that you actually put the electrons on the correct side in case you miscalculated or something like that. You know that the oxidation half reaction should be put on the right and it should be put on the left. Also, when you get to the part where you want to figure out which side you should add the electrons, you already know, because that's the oxidation, should add it to the right. That's the reduction, should add it to the left. Question on that there. All right, so now that we did that, and I'm just gonna kind of erase some of this so I got somewhere to write, I think, here, just this part of it. There's some of that there. All right, we are ready to, at this point, when we added our electrons, we are now ready to add these half reactions back together. But there is a problem, right? I can only add these half reactions back together if the electrons are the same number. Are they the same number here? They are not. My first half reaction has 1 electron. My second one has 6. That is going to require me to take the top half reaction and multiply it by 6. So I'm just going to copy it underneath. And again, we're going to multiply that 6 to everybody in the reaction, not just the electrons. So that's going to go to everybody there. Now I do have the same number of electrons in each half reaction, and we're ready to add these guys back together. So again, at this step, if you have anything on opposite sides of the arrow that are the same, they will either completely cancel out, or they could also reduce down. So they could do one or the other. In this case, as we should hopefully know, the electrons should always cancel out completely. So by electron there. And in this case, I think that is all that's going to cancel out. So we will be left with everybody on the left stays there. So we got 14 H pluses plus Cr2O7 2 minus plus 6 Fe2 plus. Now everybody on the right-hand side is going to stay on the right-hand side. That will give me here 2 Cr3 plus 7 waters plus 6 of the iron 3. Now, if I did everything correct, this is going to be my equation balanced in acidic conditions. Now, how do I know if I did everything correct? When you're done with these reactions, balanced, they has to be balanced in 2 ways, in a sense. They has to be balanced like a regular equation, which means you have the same number of elements on each side. So if we do that and we look at the hydrogen, left-hand side, there are 14. Right-hand side, 7 times 2 is 14. The Cr on the left-hand side is 2. Right-hand side is 2. The O on the left-hand side is 7. On the right-hand side, 7 times 1 in the water is 7. And lastly, the iron on the left-hand side is 6, and on the right-hand side is 6. So just like a normal equation, you have the same number of elements on each side. The second way that it needs to be balanced is the overall charge on the left-hand side needs to equal the overall charge on the right-hand side. So again here, this 14 hydrogen is going to contribute a plus 14. My dichromate will contribute a minus 2, and my iron 2 in this case will contribute a plus 12, right? So that's a lot of math there, but that's a plus 26 and a minus 2. That is a plus 24 charge happening there on the left-hand side. When I come to the right-hand side, this guy's going to contribute plus 6. This guy will contribute 0. And this guy will contribute a plus 18. Plus 18 plus 6 is a plus 24, I hope. It is balanced both with charge on each side and also with elements on each side, like a normal equation. Any questions on that there? So this would be acidic conditions. Any questions on those steps? Now, how do we do basic conditions? There are a couple ways you could do it, but the easiest way to do it by far is if you have to balance an equation in basic conditions, you pretty much just do what we just did. You do it in acidic conditions, and then at the end, you turn it into basic. So you do all the same steps we just did, and you end up with a balanced acidic equation. And now we could turn it actually into a basic. And again, here, I'm just going to get rid of some of this extra writing, so I got a little bit of room as well. So we have our steps to get to our balanced acidic. When it is basic time, we are going to add OH minus to both sides. So we're going to add OH minus to both sides. How much OH minus, you might be asking? The OH minus will be equal to the number of H pluses that you had. Yeah. So in this case, I'll rewrite it one more time underneath. 14 H pluses plus Cr2O72 minus plus 6 of the iron 2 goes to 2 the Cr3 plus and the 7 waters plus the 6 iron 3. So we have 14 H pluses in this equation. That means to the left-hand side and the right-hand side, we're going to add 14 H pluses. We're going to add then 14 OH minuses to each side. So this is what's going to turn us into basic conditions in this case. Now the side where you have OH minus and H plus, we take H plus and OH minus and put them together, what do you get? That's 2 hydrogens and an oxygen. That's also known as water, yeah? So the side that has H plus and OH minus, they will combine, in this case, of this example, to make 14 waters. And usually what will happen at this point is you will now have water on both sides. So in this case, we can reduce down the waters by subtracting the 7 waters to this side, right? When I subtract it to that side, it comes to 0. The minus 7 waters over here, we'll get rid of the 7 waters over here. And this will then become 7H2O plus everything else stays the same. Cr2O72 minus plus 6 of the iron 2 goes to 2 of the Cr3 plus, 6 of the iron 3 plus, and 14 OH minuses. And once again, if I did everything correct here and didn't mess up, there's my 2. This guy should still be balanced both ways. So let's take a look. I have still 14 hydrogens on each side. I have 7 oxygens in the water on the left and 7 more in the dichromate is 14 oxygens. I have 14 oxygens on the right. I have 2 CRs on the left and 2 CRs on the right. I have 6 irons on the left and 6 irons on the right. Overall charge, the water contributes 0. The dichromate still -2. The iron 2 is a +12. That's going to give me a +10 overall for the left-hand side. The chromium on the right-hand side is going to be a +6. This is going to be a +18. And 14 hydroxide is going to be a -14. So +18 -14 is a net of +4. +4 and +6 is a +10. So we are balanced both in basic conditions in this case and previously in acidic conditions. So this would be basic. Yeah. Question on that there. By the way, how do I know that it is basic conditions? I know it's basic conditions because what I see in the equation is OH minus. Yeah, basic conditions. How did I know the first one was acidic conditions? What was in the equation? H plus, yeah. So that's how you know it's balanced in acidic conditions or basic conditions. You should end up with H plus in your equation if it's acidic conditions, and you should end up with OH minus if it's basic conditions. Any questions on that there? Okay, we're laid up there for